Okay, so this is the Basics of AI workshop hosted by App Dev League, and I'm the VP of App Dev League, and I'm just going to be giving this presentation. So I guess we can start with what is artificial intelligence. So it's an expansive field covering a bunch of different topics like computer vision or machine learning, and all of these different things make up artificial intelligence, and it pretty much simulates parts of human intelligence, except in computers. And the applications could be in medicine, finance, hospitality, education, environmental. There's a bunch of applications. Pretty much whatever you can get data for, you can use AI in. And some modern examples are the Google Assistant, self-driving cars, and computer games have AI bots as well and stuff like that. So what is machine learning? So machine learning is a subset of artificial intelligence, which focuses on algorithms which improve from experience, which by experience is like training on data. And machine learning has pre-built libraries like in different languages like Python, such as TensorFlow, which have the models ready for you, and pretty much all you have to do is optimize them to make them fit to your data. And there's also a lot of community support. And if you have questions or you're having errors, there's really easy, it's really easy to find solutions. So when we talk about machine learning, there's pretty much two main types, which is supervised and unsupervised learning. So we can start with supervised learning, which is pretty much when your model is trained with data that has labels. And this is pretty much for two types of AI, which is classification and regression. So supervised learning would be, say you had a data set of images of dogs versus cats. Then if you have labels for all of your images, then that would be a supervised learning task. And in supervised, there's two types, which is regression and classification, which we will go further in. But regression, you wouldn't really call supervised learning because there isn't really labels, but classification is what would either be supervised or unsupervised. Now, unsupervised learning is where your model is trained with data, but does not have labels. So say you had a data set of dogs and cats, but the images didn't tell you if it's a dog or a cat. Like it was only the image, but there's no label for it. Then if you're trying to train a model on that type of data where you like even the human doesn't know what it is because there's no explicit label, then you can use unsupervised learning, which pretty much clusters the data into different clusters, right, that it finds through analyzing patterns. And there are a few different types of unsupervised learnings, but the main ones are probably semi-supervised and self-supervised. So self-supervised learning is where all of the data is unlabeled, and pretty much you have to make predictions based on completely unlabeled data. Or we have semi-supervised learning, which has a small amount of labeled data mixed with a large amount of unlabeled data. So what this would mean is pretty much, say you had the data set of dogs and cats, and say it was 100 images. Maybe for 25 of them, it tells you whether it's a dog or cat, but the other 75, it has no labels. And what the model does is using the limited amount of data that has labels, it clusters the data and then makes predictions on the unlabeled data for what label it will be. Yeah. So if anyone has questions on supervised versus unsupervised, you guys could ask them now, and then we can move on from this portion. Okay, we can go on from this then. So now, if you remember, we were talking about regression and classification earlier. We can go into that now. Okay, so with regression, you have numerical data, and it can be any number, and it completely depends on the variables. So if you remember how we were talking about earlier about dogs versus cats, where there's only two different types of things that your data can be, regression is pretty much data that's limitless, which is like predicting a house price based on characteristics of the house, right? So if you look at here, we have the price based on the area, and pretty much the price could be anything as long as the area keeps on going up, right? So it's not really confined, and we can call this continuous data. And as we said before, it doesn't really have labels. So it's not really in the supervised or semi-supervised. It's pretty much just based on certain variables like area here, predict a numerical value of your y variable, which is price in this case. And again, it can be pretty much anything. It's not really confined to any groups. It just depends on the other variables. And then the other type of machine learning we have, machine learning is classification. And there's two types of classification. So the first one is binary classification, which if you've heard binary before, it's like the prefix bi is 2, right? So it has only two types of classes, which is an example of that would be dogs versus cats, as we were talking about earlier. Or you could have multi-class classification, which is more than two, so 3 or more. And that could be maybe if you have a data set that has mice versus keyboard versus monitors, trying to distinguish between the three of them. And this is kind of what classification looks like right here. What the model does is it breaks up all of the different data into groups like this and makes predictions from that. So yeah, those are the two types of learning you can do within AI, classification and regression. So yeah, I guess now we can talk about the types of machine learning models. So probably the most basic machine learning model is linear regression, which uses a line of best fit to make predictions. So this is super basic and just uses a y equals mx plus b model to predict future values. And the only type of you could not use this on classification. It's only going to work on regression. So it's only going to work on numerical data. And if we look at this image right here, we can see that based on the data points, it makes a line, and through the line, it's going to make predictions. So this line would go on forever, and based on whatever x value it would have, it would predict the y from that. So we can look at some code here for a linear regression. We won't be coding anything ourselves because this is just an intro, but we can look at some code here. So this is just on this Kaggle website, which is a data website mostly used for data sets, but you can also host code here. So we'll just go over this notebook, and then we can go back. So pretty much in machine learning, you always have to use Python packages. So if you've worked with Python before, you probably know there's a bunch of libraries and packages that you can use. And this one is sklearn, which is pretty much all the basic models like regression. And if we look at the data set here, it has 10 variables, and it tries to predict diabetes, right? So as you can see here, it basically uses all of these variables to make a prediction. So there's a bunch of code here that if you haven't worked with these models, you probably wouldn't necessarily understand. But right here, what it does here in this block is it separates their data into train and test. And the reason we do that is because you don't want to train and test your model on the same data. You always want to test your model on data that it has not seen before to see if it actually has learned, because if it has already seen data before and it just repeats on that and keeps on testing at that, it's not really showing whether or not that if it's learned anything. So when you split the data, you can make sure that when you're testing, you're getting an actual like representation of how good it is. So right here in this is pretty much just calling the function to create the model. So this function is built in the packages that were imported up at the top. And what it does here is it just makes the model and fits it to the data and checks the score here. So in other models, there are hyperparameters, which pretty much change how the model performs. But in linear regression, there really isn't any of that. So all you have to do is just fit the data directly on, or sorry, fit the model directly onto the data. And the X train is pretty much the input data. So X is everything that you're using to make a prediction, and Y is just the prediction value. So Y train is all of the what you're trying to predict in the train data set, and X is what you're using to predict. And X test is all the inputs in the test data set, and Y test is all the predictions from the test data set. And we can see here it makes predictions on all of these, and it gives all of these scores here. And if we go down to the bottom, we can see this right here. So this is pretty much what the model is doing. So it has all of this data, and it creates a model that makes the best predictions possible on this data. So obviously there's a bunch of different data points at the same x coordinate, right? We have an x coordinate here and a y coordinate here. So if we look at this, say 150 for x, there's obviously multiple points here. So creating a perfect line is not going to be possible, but this line is the best line to make the most accurate predictions. And how this works is this line goes on infinitely, and whatever the x value is, whatever the input is, it will predict the y based on this infinite line here. So yeah, that's pretty much what linear regression is doing. It makes a line, and based on inputs, it predicts something. Okay, now we can move on to the next model. So the next model is logistic regression, and this is similar to linear regression, but it uses a more complex function. So in linear regression, it used a linear function, right? It used a line, but in logistic regression, it's a logistic function. And what it does is it separates data into different classes. So if you remember classes before, what we talked about, that would be classification. So normally it's going to be used for classification, but you can also use it for regression, which is numerical data. So if we look at this image here, this has two different data points, and it uses this function here, as you can see, this curve, to separate the data into two classes. And based on that, it will make a prediction. So we can, again, look at some code here for this. So this website is called Jupyter, and this is just a website you can use to create notebooks. And what notebooks are is they are pretty much just how you can run Python code, except you can run different blocks of code instead of running everything at the same time. So for example, this here, you could run just this block instead of running everything here. So if we look at this data or this notebook here, they make their own data set right here. If you see this, they pretty much make it into a data frame, which is shown right here. So it shows a grain size and it's trying to predict whether there's spiders, which is true or false. And when they plot the data here, it shows up like this. So based on the grain size and whether or not there's spiders present. So what the model would do is it's going to create a curve like this and separate the data into two classes. So here's pretty much the line that is created from the data. And there's a lot more stuff in this notebook that, again, you wouldn't understand if you haven't worked with these packages before, but we're just trying to get down like the main concepts, which is pretty much based on the data, make a curve here to separate it. And here we can look at another data frame here, and it looks like they're trying to predict this MPI 100 proportion based on the latitude. And as you can see, here's the curve right here. So based on the latitude and this variable, it just makes a curve. And yeah, that's pretty much what logistic regression does, is it separates data into different classes, and again, used on classification typically. And instead of a line, it's just a curve. So it's pretty similar to linear regression. Okay, so now we have another basic model, which is the decision trees. And these are yes/no trees that are used to make a decision. And based on different criterias, it can make a final prediction. And normally decision trees are used with random forest, which is a model we'll go over soon. And you typically don't use a decision tree by itself, but we can go over how it works right here. So pretty much we're trying to decide based on all these different variables whether we should play tennis or not. So the first grouping of variables here is the outlook, and we have different trees here. If it's sunny, overcast, or rain, what do we do next? So if it's overcast, we automatically predict that we should play tennis. But if it's sunny, we have to look at the humidity. And then based on that, we can make a prediction. So if it's normal, yes, or if it's too humid, we don't want to play. And if it's raining, if there's weak winds, we want to play. But if there's really strong winds and it's not playable, then we should not play tennis. So that's pretty much how a decision tree would make a prediction for classification. And it can also be used for regression, but this is the process for classification. So the two classes would be, should we play tennis or not? And that's how it makes a prediction. Okay. So this is like a documentation for this sklearn library that we kind of went over earlier. But what we can explain the code here. So what this is going on here is importing the library, and from this library import the decision tree, and you call the function here to create the classifier, and you fit it to your data just like the linear regression model. And this is pretty much the process here. So if we look at the tree here, based on all of these different values, it comes to a final prediction down here at the bottom. If you look at all the predictions, it's pretty much either this like dark green or dark purple. And if we look here, it pretty much just follows a sequence of events to get to the final prediction. So yeah, that's pretty much how a decision tree works. And they're normally used in random forests, which I'll explain how that works with random forests in a bit. So yeah, so now we're moving on to other models, and pretty much those are like the basic three models: linear regression, logistic regression, and decision trees. But there's a bunch of different models that other people have created in Python, like other libraries they've used. And example of this are like SVM, which stands for support vector machine, or an XGBoost or random forest. And an XGBoost and random forest are both decision tree type models. So we can go over these models right now. So an SVM is pretty much similar to logistic regression. And what it does here is it has this data, and it tries to create different lines to um, create different classes. So it's kind of a mix of logistic and linear regression, because you can use it for classification. As we see here, it's splitting the data into two different classes, but it uses lines instead of curves, which is why it's different than logistic. And it pretty much just creates a bunch of different lines based on the data points and where they are and how many classes there are. And this again uses similar principles as linear and logistic regression. So as we can see here, there's a bunch of different lines here to separate this red data and this yellow data. So yeah, that's the basics of an SVM. And now we can go to a random forest. So a random forest is pretty much just, so yeah, this is an example decision tree. And a random forest is pretty much just a compilation of a bunch of decision trees. So we have this data here. Pretty much what it does is these are all different trees here, as in all these different categories. And based on a compilation of a bunch of trees, we can make a final decision. And what it does is each tree makes its prediction, right? So say we have 100 trees combined for this random forest. Each tree will make a prediction, and pretty much based on whichever decision has the most, like we could say votes, right? Say each tree votes for an option. Whichever tree has the most votes, it would pick that, or not, sorry, not whichever tree, whichever option, right? Whichever out of all the classes is picked the most, it would go with that. So yeah, that's pretty much how random forest works. So the reason it's better than a decision tree is because a decision tree only has one tree to make the decision, right? But if there's a bunch of trees and you're like pretty much averaging the decisions, you can be a lot more precise and accurate for the majority of the time compared to just a singular decision tree. But those are just basic models. So what about more complex models like neural networks? So neural networks are much more complex than the previous models that we were talking about. And what they do is they simulate the structure of a brain. So all models try to simulate the structure of human intelligence, but neural networks specifically focus on the structure of a brain. And typically compared to the three basic models we talked about, they need a lot more data, and they're much better for complex tasks. And there's a bunch of different types of neural networks that can be used for different types of data. So if we have, say there's text data, right? We want to classify whether this text is happy or sad. We could use a neural network for that. Or if we had a cat versus dog, we could use it for that. So there's pretty much a bunch of different types. Whereas when we look at logistic regression, it pretty much only works on numerical inputs with the classification, right? So if we looked at what the example of the SVM, it had the size of the grains and whether their spider is true or false, right? Which is numerical data, and there's a class. but neural networks can work on images, text, audio, videos, pretty much a bunch of different things, which is why it's really useful. And you could actually test this. You could test a neural network by yourselves. So I'll send this link to everyone in the chat, and everyone can pretty much try try this for themselves, and you can try a bunch of different things. So if you can click you can pretty much try 3 different things, either image, audio, or pose. And I just have image here because it's probably the easiest. Well, what you can do here is you can add more classes, right? So classes, again, if we go back to classification, is which type like which class does the data belong to, right? So these, everything in class 1 should be the same, and everything in class 2 should be the same. And if you want to add more classes, they should be the same. So if you want to try this for yourself, what you can do is you could try to use your webcam here. So if we did, I think it doesn't let me because I have my Zoom webcam as well. But if you try this, you can pretty much do one thing. Say you had maybe just a straight face in class 1, but then in class 2 you were smiling, and then what you can do is you can train it and you can test it with your live webcam and see how well it works. So let me try turning off my Zoom camera to see if I can let me see if it allows me to. Okay, yeah, it works now. So I'll just have my Zoom camera off for a bit. But you should be able to see in my screen share. So say I had in this class, I just to record images, just hold this and just do about maybe 100 of just like a normal face here. And say in this class 2, I had one hand up like this. And we just get a bunch of images for that. Pretty much we can go to, once we've done here, you can do whichever type of classes you want, but let's just say we do that. You can go to train model here and click advanced. So this is pretty much the hyperparameters I was talking about earlier in the talk, where different things can affect how your model works. So the first thing we have here is epoch. So this is pretty much how many times the model runs through the data. So if we read this here, it says 1 epoch means that each and every sample in the training data set has been fed through the training model at least once. If your epochs are set to 50, it means the model you are training will work through the entire training data set 50 times. And generally, the larger the number, the better your model will learn to predict the data. So that is true to an extent. Pretty much how that works is obviously maybe like 10 epochs will be better than 2, but it gets to a point where the amount of epochs doesn't really matter. But yeah, you could definitely mess with this to see if you could get better accuracy. Then here we have batch size, which is another hyperparameter which affects how good the model is. So if we look at batch size, a batch size is a set of samples used in one iteration of training. For example, let's say if you have 80 images and choose a batch size of 16, this means the data will be split into 5 batches. And once all 5 batches have been fed through the model, exactly 1 epoch will be complete. And so you might be wondering, why does that matter? Like, what's the point in splitting up the data? So pretty much how it works is for each batch, after it finishes one batch, it makes adjustments to the model for the next batch to try and get improved accuracy. So pretty much depending on your data size, you'll want to choose your batch size. So if you have a bunch of data, then you probably want your batch size higher. And this is also going to affect your how long it takes to train a model. Obviously, this will be pretty quick because it has like, I believe it's running on like Google's servers. But if you have your own model running on your own computer, then if you have a super low batch size, it's just gonna have to keep on going and going and going, splitting your data. So that's gonna take a really long time. But if you have a smaller amount of data, it's good to have a lower batch size, and if you have a higher amount of data, it's better to have a higher batch size. Now we can go to learning rate. So learning rate. So it says be careful tweaking this number. Even the small differences can have huge effects. Normally, you could just leave this alone because you'll probably get the best results on the default. And yeah, so those are pretty much the 3 given here, but there's a bunch of different other when coding your own neural network, how it works. So if we can train this model here on just these default hyperparameters, and let's see how that goes. So yeah, you can try this out for yourself with whatever data you want. Wait here, I'm gonna turn off my screen share for 1 second. I think it's causing some issues. I'm going to train the data and then I'll turn the screen share back on as soon as it's ready. But yeah, in the meantime, feel free to try your own classification and see how that works. Okay, I'm getting this. It says, hold on. I'm going to try to retrain it again. But yeah, if your guys' training works, then let me know in the chat how that went for you guys. I'm gonna try and train again, and then I'll turn on my screen share again. Oh, okay. You were able. Yeah, I see that. I got your screenshot. Okay, yeah. So you uploaded images. Yeah. Let me. Okay. Yeah. Using the webcam is not working for me, but I can. I'll. Okay. I guess since we had one in the chat already, we can just move on from this one because my like Chrome is just crashing when I try. So now we'll go over code for a neural network. Here, let me turn on my camera again. So yeah, let me pull that up and then we can go over code of for that. Okay. Here is the. All right. So this is pretty much this is a notebook I made for neural networks, and pretty much what we're trying to do here is predict whether someone is at a high chance of a heart attack or not. And there's a bunch of different data properties here, but pretty much we have the output here, which is either 1 or 0. So 1 is high chance and 0 is not. And then there's a bunch of different things here like blood pressure, the chest pain type, which is like 0 to 3, cholesterol, blood sugar, stuff like that. And here's pretty much where the neural network comes in. So this is pretty much a function from the package right here, which again, if you've worked with packages in Python, you probably know they have built-in things that you couldn't do in normal Python. So this is something that's like that. It's pretty much calling a function which creates a model. And this is just adding layers here. So the way a neural network works is you have the first layer, which is an input layer. And what it does is it takes in the data. And then you have layers in the middle, which make the predictions and optimize the model to be able to make good predictions. And then you have an output layer, which just makes the predictions for the final predictions, right? So if we look at here, we have the input layer right here. And what it does is it takes in the data, and this right here is just the amount of neurons in the layer. And here we have the middle layer, which is called the hidden layer. And then at the end, we have the output layer, which makes the predictions. And then we have our optimizer here, which there's a couple different optimizers, but pretty much what they do is just make the model more accurate when you're training it. And then, yeah, and pretty much you fit the model to the data, the X-train. Again, if you remember, we talked about that earlier. What the X-train does is it's just the training, the input training data. Y train is the output, which is what you're trying to predict. And if you look here, this is what was in the teachable machine one, the amount of epochs and the batch size. So this is 200, which means it ran through 200 times, which you can see here. And the batch size again is how many you split the data into per epoch. So yeah, this is it for the heart predictions. And here we have a neural network for images. So what this is trying to do is predict what this handwritten digit is. And this is a really common data set, which is called MNEST, which is pretty much just like a set of hand written digits. And you can get it from the actual Python package itself. And it's this, as you see, this model is super similar to the other neural network, which was for the heart predictions. You have the input layer here, which you can see this input shape here. Pretty much is just the size of the image, so 28 by 28 pixels. You have the hidden layer, and then you have the output layer. And yeah, this one we didn't set we didn't set the batch size here, which if you don't set the batch size, what it does is it doesn't cut through the data at all. Which means like, so if you remember, if we had a batch size of 16, right, and we had 80 training samples, it would cut the data into 5 groups. If you don't set a batch size, it just keeps it in one group. So yeah, and 3 epochs here. It just runs through the data 3 times, and yeah, you can see the accuracy here and everything. So yeah, that's it for the neural network code. Okay, yeah. Do we have any questions on neural networks or this teachable machine here? Because if that was kind of fast, then we can go over it again if anyone's wondering. And you train, I mean, honestly, if you had something like, you could definitely train an AI model to distinguish between someone who is like awake or someone has their eyes closed. So if you had like something that, I don't know, if it detected that your eyes were, or like you were sleeping, that like played an alarm or something. But yeah, there's pretty much you can train AI to do anything that you could find data on. And yeah, but the issue with finding data from online is that it may be incorrect, because pretty much like if you remember the Kaggle website that we went on earlier, that's pretty much definitely one of the bigger websites to finding data that other people make. The issue is anyone can just put up data there, so like there's no one really checking whether the data is correct or if it's labeled correctly, right? So say if you had, say on the Kaggle there's a data set of cats versus dogs, and you had one folder of cats and one folder of dogs, like there could definitely be images in the wrong folder or something like that, and no one would really be able to, I mean, unless you went into the data and saw everything. So that's kind of the issue with finding data online. But yeah, pretty much anything you can find data on, you can do it. And once you really understand what like how it works. You don't necessarily really need to know the math behind like these neural networks, but if you just understand the concepts coding it, it's not that hard because um the syntax is there's always like the syntax is always online. How you write the code is always going to be online. You don't really need to memorize it. As long as you understand what you're doing, you'll always be fine. A universal Turing machine. What does that mean? A universal.
It's a machine that essentially detects if the code it's being given will break down and not be good.
Oh, that's interesting. I think I don't think that would necessarily be an AI task. I feel like that would be more of just something that you create that maybe runs through the code. You don't necessarily need to learn anything. And I don't it kind of depends. I feel like you could definitely do that without AI, just like a normal algorithm. So yeah, that's kind of the difference between just normal algorithms and AI, which is like something that's going to be different every time, right? So if you had like code that's not going to work, then you would know the code wouldn't work, right? Like if you ran the code, it wouldn't work. So you don't really need to learn anything from there. So definitely just a normal algorithm would probably be good enough for that. Yeah, so you can Yeah, so I think the last thing we have here is just evaluation methods for models. So the three main ones or for different types of evaluation is accuracy F1 and area under the curve or AUC. So pretty much based on what you have, you're going to use one of the three of these. Um, so accuracy is just how many times your model predicts the correct class. And the reason you can't use it on all data, it might seem like, oh, why not just use accuracy all the time? Um, the reason is because obviously some data you have that is like the regression, right? The numerical, which obviously say you had a house that's like you're predicting the house based on the size or how many bathrooms, how many bedrooms. Then say it's like maybe $300,000, right? And you predict $300,005, right? Or $305,000. Then that's pretty much correct for the AI model. It's pretty good, but if you were to run accuracy on it, it assume it's wrong, which is why you can't really use it on this continuous type data. And it's a lot better for stuff like image classification or like the heart prediction, whether there's a high chance or not. But a reason you wouldn't use accuracy is say you had a lot more data of one type than another. So say we had 100 images and 80 of them were for dogs and 20 of them were for cats, then pretty much accuracy, if you guess a dog every single time, that's 80% accuracy, right? Which obviously isn't terrible, but that doesn't really mean anything, right? Because you're just guessing the same one over and over again, which is why you don't always want to use accuracy. It really depends on your data. So for that type, you'd use area under the curve, and pretty much how this works is it has two curves based on your model, and it looks at how much of the area of the curves are overlapping, and it's a value between 0 and 1, and the closer to 1 it is, the better, and the closer to 0 it is, the worse. So if you have like an AUC of maybe 0.8 or 0.9, but you had an accuracy of like 70 or 80, then you might think an accuracy of 70 or 80 is pretty bad. But then if you have the area under the curve of 0.8, that's actually pretty good. So yeah, it really just depends on your data. And then also we have here is F1, which is just a combination of precision and recall. So precision and recall are two different types of things you can use for classification, and it just pretty much combines them to make a better, more holistic evaluation method for that. So yeah, do we have any questions on the evaluation methods? Okay, if not, I think that's it for us. So if you have any questions for us, you can always ask us at AppDev League, which is pretty much we have a bunch of content for stuff like this. So if you had any questions for that, feel free to ask us. And yeah,
Okay, great. Thank you so much for doing this workshop. It was amazing. I hope everyone learned a lot, and maybe we'll apply it to their project in the next couple of days. So yeah, thank you so much, and bye everyone. We're playing Among Us in 30 minutes, so come hang out with me. We'll play some games. It'll be fun. So look out for a link in the announcement channel.
Thank you. Bye.
Thank you. Bye.